The last exercise in the module and the last class of malware are rootkits. The discussion will cover the definition of rootkits and methods for detecting them. A rootkit is not necessarily a malicious or harmful program. It's used to hide the existence of some process from users and administrators. What can be hidden using modern rootkits? This category can include other programs or their payloads in a system. Also, internal system mechanisms can be hidden, as well as services, files, directories, user accounts, and active network connections. A rootkit can hide anything, really. This doesn't make it malicious per se. Unfortunately, it is often used to conceal the existence of programs that can harm your system. Historically speaking, the first virus, Brain, made use of stealth techniques as well. It wasn't strictly speaking a rootkit. It didn't attempt to hide other objects, but it did take cover in a system. Rootkits have a relatively long history. The first rootkit was written for Unix in the 60s. The solution employed for the program was very simple. It aimed to replace Unix systems' tools for displaying files, directories, and processes with utilities that did not display some files or selected processes. Rootkits have come a long way since that time. Rootkits can be divided into 3 subgroups based on their working principle. The first group of rootkits are designed to hook user interface but not the kernel. They execute in a user mode. The second class of rootkits alter kernel processes. The third group modify data structures under the kernel's API. These rootkits run at the lowest level. Let's now discuss each type. Let's start with user mode rootkits that hook user API. Imagine that a user launches Windows Task Manager. The program is used to display active processes. To perform this function, the application calls a Windows API function implemented in the NTDLL library. If a rootkit is placed in this library, Task Manager would receive only selected information instead of information on all active processes, Explorer, WinLogin, and malicious malware exe. The information that a rootkit is trying to hide is filtered in the user mode. What are the strengths of user mode rootkits? Above all, they can be run and executed without administrator permission. A weakness for an attacker is that rootkits that hook a user API are easy to detect. We'll show possible detection methods in a minute. The popular Hacker Defender is an example of a user mode rootkit. The free demo version of the rootkit is still available at www.rootkit.com. It used to be developed extensively, and personalized versions were sold for more than $100 per item. The official free version of the rootkit was easily detected by antiviruses and rootkit detectors. A tailored version was practically undetectable. You could also buy a rootkit subscription from the vendor that guaranteed that the rootkit would not be detected for 6 months. The second type of rootkits are kernel mode rootkits that hook the kernel API. Let's go back to the example given before. A user or administrator wants to display a list of active processes. This time the list is not filtered user-side, but in a system function call. A rootkit operates kernel-side and filters the calls by modifying kernel API. Kernel mode rootkits are much more difficult to detect, which makes them more effective. A drawback for attackers is that they require administrator permissions to run. Writing kernel mode rootkits takes a lot more skills than other types of rootkits. They can be an example of malware that has been blocked, at least for now, through the use of defense mechanisms such as the requirement to assign modules in Kernelmode drivers, or technologies that prevent patching the kernel. NT-rootkit is a popular rootkit of this type. It was created by the webmaster of www.rootkit.com. A third type of rootkits that execute at an extremely low level and are quite complex are rootkits that directly modify kernel data structures instead of kernel interface. This makes rootkit code invisible even from the kernel, but it's still run. A system has to assign CPU time to the rootkit from time to time, or the rootkit wouldn't have a chance to perform its function. The cloaking is not performed by filtering API, but in hiding directly in the kernel. An example of a rootkit of this type is the aptly named FU rootkit. Thank you.